and making a link to the Sundhedsstyrelsens handicapped baby thing. Just a little link. Mean and variance. I think we in a way we discussed it a little bit already. The thing is, last week I told you how to compute the average, or sample mean, we could call it, and the variance, the sample variance and sample standard deviation, when we have some numbers. Actually, when we have an unknown probability system, we can also compute what could be called the mean and the variance, actually, at least if we know the probabilities, right? This is just saying that when I throw 10 times with a symmetric coin, my expectation to the number of outcomes would be 5, right? In the long run, I would get half of it as the outcome. That's the expected value. One can compute such an expected value just out of the probability function. So if I know the probabilities of a random system, and that goes, this is very general, it goes for all discrete systems. I'm just using the binomial as the example. And it goes like this. The mean or expected value of the random variable in an arbitrary discrete random system is all the possible outcomes weighted by the probability that they will appear, right? If it's the dice, I don't think I have it, but yeah, I have it, fantastic. Here's the expected value of one dice throw, right? 1/6 probability of getting the 1, 1/6 of the 2, 1/6 of the 3. All the 1/6, that's the small f, that's the probabilities. And the expected value on the long run, if I throw one dice, would be 3.5, right? So the expected value can actually be a point outside the possible sample outcome space, funny enough. But if you think about it, it's pretty clear. I'll not do this now, I'll just show it to you. We could, of course, compare that with actually looking at the mean of certain outcomes, like I talked about with the coin before. It would not match exactly, at least not for small n. For a large n, it would. I have a slide on that. Here it is. It looks very complicated. This only says, if I do 1,000,000 throws with a dice, then I'm very close to seeing completely equal proportions of 1s, 2s, 3s, 4s, 5s, and 6s, right? That's what this statement says, and if n goes to infinity, if I do a transillion, it will be 1/6, 1/6, 1/6, right? Maybe more challenging for you, but very important for you to think about, is the fact that any random system that hits us in the face, also looking at number of handicapped babies born in Denmark, will constitute variability. The system will have a variable outcome. The random variable will not give you the same result each time. So we need a way to quantify the variability of a system. How different can the observations be from time to time? And that can be done theoretically like this. And this is the theoretical definition that matches exactly the sample definition of a variance I gave you last time. Because now I still away with the probabilities. And in the dice case, it's 1/6, 1/6, 1/6. That's the 1/n thing, that's the averaging thing. But then I'm taking not the average outcome, but I'm taking the average of the squared deviation, right? I'm taking the average squared deviation from the mean. That's what I did last time when I computed a variance on numbers also. I computed the average, I took each number, I squared, I averaged. That was the definition of a variance. Here is a formal definition within the context of a discrete probability system, a discrete random variable. And to make an example, for the dice, we take each deviation from the mean, start by computing the mean. They are weighted by this. You can see if it's the unfair dice, we can do a similar computation. That's very easy. We just have to do 1/7, 1/7, 1/7, and then 2/7. So that works for any case. It can be compared with the actual numbers there. 3 slides at the end showing you that if you take those three distributions that I now presented to you, the binomial, the hypergeometric, and the Poisson, you can deduce analytically what the mean and variance is. So you can take the theoretical probabilities. Here is the and you can plug them into this one, and then you can look at the sum and you can actually find what it is. And also this, here's the variance again. You can plug in and you can see what it becomes. That's a mathematical thing I'm not going to spend time on now. I have some extra math videos where I show some of this, if you're interested. It's not syllabus to make those proofs. So in the binomial we get what we already knew, or felt like we knew. That on average, of course, the mean of the binomial is NP. If I throw 10 times with a 50-50, it's 5, of course. The variance of the binomial, that is what Sundhedsstyrelsen used to show this band on the curve that I showed you. Actually, we'll get back to that later in the course where I give you the exact formula for how to do this. Now I'm just making the point. The variance of a binomial is NP1 minus P. That tells you how different should you expect numbers to be from year to year when I count how many disabilities do I get. That's an important number to be intelligent about looking at the number, right? Because otherwise you would, one year you get an increase, and if you're a politician and you don't know about variances, I'll let that hang in the air for a sec. If you're a politician and you don't know about variances, I would say 177 or 179. Oh, sorry, I'm being recorded, so I should be careful about what I'm saying. Of course, we are happy about our new Minister of Science. I love you. Let's have the Fremdriftsreform changed as fast as possible. Oh, I shouldn't make any political statements here, so cut it away. Anyway, I forgot my point now because of all this. We use the variance, and that is very important. Here's the point. Yeah. Thank you. If you do not accept and realize something called variability, then if you were a politician and you decided about the money, so one year you see an increase in the number of disabilities, let me throw $1 billion in that direction for us to be better on that. And then the next year you see a decrease. Oh, I'll take the $1 billion again and throw it somewhere else where I see a random fluctuation, right? It's not good if we have too much of that kind of money priorities in our systems, right? We shouldn't throw money after random fluctuations. We should throw money after something that we know is important. In the business, it's exactly the same thing. If you throw money after random fluctuations in business, you might be doing good 1 year or two, but then when the fluctuation goes the other way, you're done, right? We have formulas for the hypergeometric, for the Poisson. They are there. If you need them, you can find them in the material, so you can work with means and variances there also. That was it. But don't leave, don't leave, don't leave. We have a single little thing to finish off. Let's just see how you did. %40 of you will pass the course. I mean, I'm not going to spend time on looking at all of this where I ask you how you study and all. I'll just have a look at it afterwards. But the one thing I would just look at was the single question at the end. Let me see. Fast, plus, hand, move. Which statements are correct? Yes, those of you, you saw it. The discrete density function expresses probabilities. Yes, that's correct. A random variable can always only attain 2 possible values. No. That's an example, but random variables can attain any kind of values. The distribution function and the density function are not related to each other. Yes, they indeed are related to each other. They are, you can get explicitly, we saw that the definition of the probability distribution function was given explicitly by the explicit densities. And in fact, the other way around, you can get the small f densities from the capital F1. So if you have complete little f, you can get complete capital F. If you have the complete capital F, you can get the complete little f. They are two alternative characterizations of the system, just as good because you can get one from the other. So, stating that they are not related is rubbish. The distribution function expresses accumulated probabilities, and we will, of course, that's the reason why we discuss this, we are going to use the right probability thoughts and insights to what the variances are. That is the core insight we're going to use when we are going to, in 2 weeks, really start looking at numbers in this course, which is the purpose of stats. So that was the third correct answer. Many of you had that one correct without some of the others. But hey, I'm glad you're playing in with me and enjoyed over there. Thanks, we're done.